Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue thinking about earth materials. So this is going to correspond to section 4.3 of your textbook. So the next thing we need to think about is how do we distinguish one mineral from another, because that's got to be one of the goals of a geologist. When we look at a rock we need to know what we're looking at, so obviously we need to be able to work out what the minerals are. So what are the various criteria that a geologist can use to try and identify a mineral? Well, the first criteria we can use is the crystal form, or to put it another way, the crystal shape. Now, a lot of crystals in rocks will be highly irregular in their shape, and so we can't really use the crystal form, but if we happen to have a crystal that has quite a nice, well-formed shape to it, we can sometimes use the crystal form to help us identify it. So you can see in this particular example we have three separate crystals, and you can quite clearly see they have very distinctive shapes. So this one is approximately a cube in shape, so we refer to that as a cubic habit or a cubic form. In the case of this crystal here, it has a shape a bit like a tablet, and so we'd refer to this as either a prismatic crystal or a tabular crystal. And then we have this crystal here, which as you can see has this columnar shape, but you can notice this column has a hexagon, so we'd refer to that as a hexagonal form. And so certain crystals will display certain forms. So for instance, I might know that the mineral pyrite, which is also sometimes referred to as fool's gold, will very often occur as cubic crystals that look like this. And so that's something I can keep an eye out for. And so crystal form, although only helpful when you have nice, well-formed crystals, so they're very nicely proportioned, can be very helpful, but if you have irregular crystals, unfortunately, it doesn't really do you that much good. Now, the next thing that we can look for is something which geologists refer to as cleavage. So cleavage is the capacity of a rock to preferentially split along a plane of weakness, and these planes of weakness are referred to as cleavage planes, and the rock will naturally want to split along them. And so as you can see in this particular instance, we have two different samples of minerals. So over here we have a couple of mica minerals. At the top here we have the mineral muscovite, and at the bottom here we have the mineral biotite. Now the thing you'll notice is you can notice the top of both of these samples are amazingly smooth. And this is because both of these minerals, the muscovite and the biotite, have cleavage. And remember, the cleavage is a plane along which the mineral will preferentially break. And because it wants to preferentially break along that surface, when it does fail, it will leave behind typically a nice smooth finish. Now compare that to this quartz crystal here, which does not have cleavage, so there's no preferential weakness along which a mineral will want to break. You will notice that essentially you don't see any nice smooth surfaces. In fact, the sample we can see here just looks like a piece of broken glass, because there's no preferential plane along which the mineral will split, so it just splits in any random direction. Now, in terms of cleavage, you can have more than one cleavage, so you can typically have anywhere between 1 or 6 cleavages, and that will vary depending on what mineral you're looking at. But you can also look at the orientation of the cleavages. So if you have more than one cleavage, you can look at the angle at which those cleavages are intersecting each other. And so the presence of cleavage, the number of cleavages, and the angle at which these cleavage planes intersect one another can all be used to help us identify minerals. And to be honest, this is one of these diagnostic features that's extremely helpful to geologists. If you can find cleavage in your crystal and you can identify them, then it's a really good guide to help you try and work out what mineral you're looking at. Now, the next criteria we can use is colour, and I'm going to be honest right now, typically trying to identify a mineral using its colour is a bad idea, because a lot of minerals will have variation in their colour depending on very, very minor chemical changes. So for this particular set of minerals down here, we can see we have what are referred to as varieties of the same mineral. So these are varieties of the mineral quartz. So at the back here we have what's often referred to as rock crystal. So this is a nice clear crystal of quartz where it's it's transparent. You can light passes through it. It looks like a piece of glass, for want of a better way of describing it. Now compare that to this crystal here, which has this purple colour. Well, this is the variety of quartz which we refer to as amethyst, and the purple colour is the result of an iron impurity in the crystal that's been lightly irradiated. And so the presence of this iron impurity and the small amount of radiation that it's been exposed to has produced this rather distinctive purple colour. So once again, in this case, still the same mineral, but a very, very, very minor change in the mineral's chemistry has produced a change in colour. In this case over here, we have a piece of what's referred to as smoky quartz. It has this rather grey look to it. This is the result of radiation damage. This particular quartz crystal has been exposed to radioactivity, and so it's gone and damaged the crystal, giving it this rather smoky appearance. Then at the front here we have what's often referred to as cloudy quartz, and these quartz crystals have this rather cloudy appearance because they contain lots and lots of very, very small bubbles of fluid trapped inside the crystal. And these fluid inclusions which are in the crystal are numerous. There'll be, thousands of them, tens of thousands, maybe even millions of them in the crystal. And their presence in the crystal means that it doesn't have the same, transparent appearance as the rock crystal back here and the crystal back here. Instead, they have this rather creamy look to them. So colour is highly variable depending on chemistry, but it can also vary due to other factors such as radiation damage and also the presence of inclusions within your crystal as well. And so it's not uncommon for the same mineral to be to occur in numerous different colours. Now there are some instances where colour is quite helpful. A classic example of that would be the mineral kyanite. Now, kyanite is a mineral that has a rather distinctive blue colour to it, and there aren't many blue minerals out there. And so when you see a blue crystal in your rock, well, in that situation you think to yourself, okay, there's a good chance this crystal may well be kyanite. But, on the whole, colour is a dangerous diagnostic feature to use because colour is variable in a lot of cases. The next thing we can use is luster, and luster essentially says, how does the light reflect off the surface of a rock? Now, if we look over here, if we go back to this crystal at the back of the image here, we can see that it looks like a piece of glass. So this is referred to as a vitreous luster. The mineral has a glassy appearance to it. Now, vitreous luster doesn't just apply to materials that have this glass-like look to them. It will also apply to materials like the cloudy quartz at the front here. And that's because if you imagine you had a block of glass and it was frosted glass, the way the light would reflect off the block of frosted glass would be similar to these creamy quartz crystals that we can see at the front. So a vitreous luster, is simply the light will bounce off the surface of a crystal as if it was a piece of glass. We can also see we have other lusters like this luster here. This is referred to as a metallic luster because the mineral looks like it's made of metal essentially. The light bounces off the surface as if it was a piece of steel, for instance. And so, these minerals that do have these metallic clusters are quite easy to spot because they have a metally appearance to them. You can also have minerals that have an earthy look to them. So they look like a bit of dry soil. And so when the light reflects off those, they will often have quite a dull appearance to them. And then you can have certain lesser lusters, so things like a pearly luster, which is when the light essentially has a kind of gives the mineral a pearly appearance, and that's typically because the mineral in question is made up of lots of fine layers, and so the fine layers mean that as the light enters the crystal, it means it gets refracted and deflected around inside the crystal, and it gives it a kind of pearly iridescence. And a good example of the type of minerals that might have a pearly iridescence would be something like the two mica minerals up here. We've got the muscovite here and the biotite here. They have lots of thin layers, so as the light enters the crystal, it will get bounced around inside the crystal, and it will give the crystal a kind of iridescent pearly appearance. And so luster is extremely helpful to geologists. When we have something that has a metallic luster, typically it's very, very obvious and easy to see. Vitreous luster is by far and away the most common luster, so lots of minerals have it, but nevertheless the presence of a vitreous luster is also a good identifying feature. You know, if I see a rock with a vitreous luster, yes, there may be thousands of minerals that it could possibly be, but at the same time I've also managed to eliminate a whole group of minerals that do not have vitreous lusters. Same goes for earthy lusters. Once again, when I see a mineral with an earthy luster, it helps me to reduce the possible pool of minerals which I could be looking at. So the things that geologists will be looking for, on this slide at least: crystal form, cleavage, colour and luster. Now, geologists can also look at a number of other factors. So the other factor we'll look at would be something like hardness. Now, hardness in geology is based on what's called the Mohs hardness scale. And it's a scale that runs from 1 to 10. Number 1 on the scale is the mineral talc. That's the stuff that talcum powder is made from, so it's very, very soft. And at the other end of the scale, we have the hardest naturally occurring mineral, which is diamond. And the Mohs scale is helpful to geologists because it uses a number of materials to test the hardness which will be readily available to a geologist. And so, for instance, we will use our fingernail, so minerals which are 1 or 2 on the scale will be scratched by a human fingernail, but a mineral that's 3 on the scale or higher will not be scratched by a fingernail. A mineral that's 3 on the scale will be scratched by a copper penny, but a mineral that's 4 or higher on the scale will not be scratched by a copper penny. A mineral that has a hardness of 5 or 6 will be scratched by a steel nail, but anything 7 or above will not be scratched by a steel nail. And then, of course, anything that's 7 or higher will scratch glass. And so geologists will often go out into the field with, obviously you've got your fingernails, you'll take a copper penny with you, you'll take a steel nail with you or a knife, and you may also take a small piece of glass as well. And you can use these in the field to actually work out what mineral you're looking at. And because hardness is one of these factors which is very, very helpful to geologists, because even if so if I just go back to it for a second, all of these quartz crystals here are all going to have exactly the same hardness. They have a hardness of 7 on the Mohs scale. So this is extremely helpful to me. So when I do my tests on the crystals and I say, right, well, they fall at a number 7 on the Mohs scale, that allows me to once again eliminate a whole range of minerals which it cannot be. So for instance, if I have a crystal like this, there's a whole range of different minerals it could be. So let's say it could be something like halite, which is known to us as salt. Well, halite can look like this. It can be nice, clear, transparent crystals. And so, am I looking at halite? Am I looking at quartz? Well, halite has a hardness of 3, so I can scratch it with a copper penny. Quartz has a hardness of 7, so I can't scratch it with a copper penny. And so simply by taking out a penny from my pocket and just using it to see if I can scratch the mineral, it gives me an idea of what mineral I might be looking at. So I can eliminate a whole range of minerals which it is probably not. So hardness is definitely one of those factors that geologists will use on a regular basis to help us identify certain minerals. Now, the next thing we can use is effervescence, which essentially is, does the mineral react with acid? Now, in the case of geology, we typically refer to effervescence as being based on the use of just one particular type of acid, and that acid is 1 mole hydrochloric acid. Now, obviously, depending on what mineral you have, you can dissolve it in a whole range of acids. So certain minerals will dissolve in nitric acid, certain minerals will dissolve in sulfuric acid, certain minerals will react with hydrochloric acid. So in geology, though, we typically just stick to one acid, so we just focus on hydrochloric acid on the whole. And so when we're talking about effervescence, what we're actually saying is will the mineral react with hydrochloric acid? And to be honest, the vast majority of minerals will not react with hydrochloric acid. However, there is one group of minerals that will, and those are the carbonate minerals. And the carbonate minerals, which we'll be discussing later, will readily react with acid. So when you put the hydrochloric acid on top of them, you will see the mineral bubbling as the chemical reaction happens and carbon dioxide gets released as a byproduct, producing the bubbles that we can see. So the presence of effervescence, the presence of a mineral that reacts with acid, tells us instantly that what we're looking at is probably a carbonate mineral. And so that instantly means we can discount a whole range of minerals and just focus in on the carbonate minerals. And at that point, we then just have to work out, right, which carbonate mineral am I actually looking at? Now, the next feature we can use is something which is referred to as streak. Now, this white thing here is a streak plate. So it's made of ceramic and it's very, very hard. And it's designed for you to drag a rock over and leave behind a streak of the rock on the plate. Now, streak is typically something that you will use on minerals which have a metallic or submetallic cluster, so they look like metal. Okay, you will typically not use streaks, a streak test on a mineral that has a vitreous luster. So you wouldn't use it on a mineral like quartz. You would instead use it on a mineral that has a metallic appearance, so something like pyrite, which is the mineral which we also refer to as fool's gold. You could maybe take the streak. Now you're thinking, well, why is the streak useful? Well, when a rock like this is in your hand, typically what you'll see is the crystals will often all be orientated in approximately the same direction. Now this means that when the light hits the rock, it will give the rock quite a uniform appearance. So if I just go back to the previous slide, here we go. This crystal here, the one in the middle, is a crystal of the mineral galena, which is lead sulfide. And you can see it has this nice metallic luster. Now, because the crystal itself all has a nice consistent orientation, when the light hits it, I get a consistent response from that light bouncing off in a consistent way. And so the colour is, one more time, consistent. And so it has a homogeneous appearance to it. Now, as soon as I take that same rock and I drag it over a streak plate, what I end up doing is I end up making a powder that consists of lots of crystals which have random orientations. And so this means the light bouncing off this powder will not have a nice homogeneous appearance, and so sometimes it can produce a distinctly different colour. So the classic example is the mineral hematite, which is an iron oxide mineral. Now, when you have a really nice, well-formed crystal of hematite, it will have a very dark, black-grey metallic appearance to it. So, it looks like a very deep grey mineral when you look at it as, in a nice, well-formed crystal. However, the second you take that hematite crystal and you drag it across a streak plate, it produces a very distinctive rusty red streak, which is the colour you can see right here. And so there are lots of minerals which are metallic and have a grey colour. However, there's only one mineral that has a dark grey metallic appearance but gives a rusty red streak. So as soon as I take that piece of hematite and I drag it across the streak plate and it produces that rusty red streak, I know exactly what mineral I'm looking at. And that goes for a range of metallic and submetallic minerals. You can drag them across the streak plate and it will leave behind a streak that has a very distinctive colour, and it will help you to work out what mineral you are looking at. The next feature we can use is magnetism, and this is a really helpful one because there are very few minerals which are actually magnetic. And so if you do come across a mineral that is magnetic, well, instantly you can really move towards a very, very limited group of minerals that it could possibly be. So there's only really two minerals which are magnetic and pretty common. The first one is the mineral magnetite, which is the mineral you can see here. It has this kind of metallic appearance to it in this medium to dark grey colour. And the other mineral is a mineral called pyrrhotite, which has a kind of brassy yellow colour to it. So it's quite easy to distinguish between the two of them. So once you know the mineral in question you're looking at is magnetic, well then you think to yourself, right, what minerals could it be? Chances are it's either going to be magnetite or pyrrhotite. And so then you just look at the colour. Is it grey? It's magnetite. Is it kind of like brassy yellow? It's pyrrhotite. Done. So magnetism, although not useful on the vast majority of minerals, when it does occur, it's an extremely good feature for working out what mineral you're looking at. So the final feature we can use is a mineral's specific gravity, its density. How heavy does the mineral feel? Now, once again, in most instances, this doesn't really help us. So the vast majority of minerals are a group of minerals which we refer to as the silicates, and they typically have a relatively similar density. And so that means when you compare one silicate mineral to another, you can't really feel any difference in weight. However, there are certain circumstances when the difference in weight will be quite noticeable and therefore helpful to us. So one of the classic examples is the mineral barite. Now, barite is a barium mineral, and if you know where barium sits on the periodic table, it's down in the bottom left, so it's quite a heavy element. So barite, because it contains barium, is also going to be quite a dense mineral. It's going to have quite a high specific gravity. Now, barite has a kind of, normally has, shall I say, a rather creamy white appearance to it. So it actually looks quite a bit like the cloudy quartz here. Has a similar appearance. So the question is, well, how do you tell the difference between the quartz and the barite? Well, it's all down to the specific gravity. So because barite has barium in it, it's going to be a very heavy mineral. And the second you pick it up, you will naturally feel the weight of the crystal, and that's instantly going to tell you, right, this is probably not a crystal of quartz. This is probably something that has a heavier element in it. And then as a geologist, I will think, right, what are my possible options? And I'll try and work out the mineral from there. So these are the general criteria that a geologist will use when trying to identify a mineral, and we will often try and apply as many of these different criteria to any mineral that we come across in order to make sure our identification is accurate. Alright, thank you for watching everybody, and have a good day.